Hello friends, welcome to the another tutorial of basic electronics module. Today we are going to learn about logic gates. That what are logic gates? I know many of you are unknown to logic gates and many of you don't know anything about the logic gates. So today we will explore these different gates and where they are used and why they are important. So, in this chapter, you are going to learn the basics of logic gates. And this is particularly my favorite and also an interesting one session. So, let's see the table of contents. This particular chapter is divided into four different parts. In first part, we will see the introduction to logic gates and their applications. In the second part, we will see the three basic gates, which are OR, NOT, and AND gate. In the third part, we will see NAND and NOR gate. And in the fourth and last section of our session, we will see XOR and XNOR gate in detail. So let's start our today's session with the introduction part. So what are logic gates? Many of you would have this question that what is this, that what are logic gates. So let's first see that what are these logic gates. So a logic gate is an idealized or physical device that performs a boolean function. So in short you can say these logic gates are devices are used which are used in digital systems. So these are the devices which performs logical operations. They are operates on logical operations. So these are the devices that performs a boolean function, a logical operation performed on one or more binary inputs. Means one or more binary inputs that produces a single binary output. In real world, the primary way of building logic gates uses diodes or transistors acting as an electronic switch. Today, most logic gates are made from MOSFETs, means metal oxide semiconductor field effect transistors. These logic gates are used to carry out logical operations on single or multiple binary inputs. Means in inputs you can have more than one quantity, but in the result you will get only one output. In simple terms, logic gates are the electronic circuits in a digital system. So they are widely used in digital systems. Now let's see their applications. Where are this type of logic gates are used? So they are used, or you can say they are mostly found in the circuits such as safety thermostats, push button locks, automatic watering system, light activated burglar alarm, and many other electronic devices. You can see the different logic gates. So, after seeing the applications of this type of logic gates, let's see there which are the different types of logic gates. So, there are different types of logic gates used in performing operations in digital circuits or digital systems. The common ones are OR gate, AND gate, and NOT gate. Additionally, these gates can also be found in combination of one or two, means combining OR gate, AND gate, and NOR gate. With each other, you can get different gates also. Therefore, we get other gates such as NAND gate, NOR gate, XOR gate, and XNOR gate. So, using or combining the NOT and AND gate, you will have NAND gate, means NOT and AND, combination of NOT gate and AND gate. Now combining NOT gate with OR gate, you can have NOR gate. Also XOR and XNOR, these are the two different gates of logic gates. Now these logic gates are made to perform different logical operations in digital systems. So as we have discussed their types, you can see that these are the logical operators and they are named according to their operations. So in OR gate, there would be a logical operation such as or in the input side or in the inputs in the input there will be an operation such as logical operator or. In AND gate, the input performs logical AND operation, and in NOT gate, the input performs logical operation of NOT. So this is how these different logic gates are named. It operates on logical OR operation. This gate operates on the logical operation and this particular gate operates on the NOT operation. So this kind of logical gates has one or more inputs, but they only have one output. But there is a special gate which has only one input and only one output, and that gate is NOT gate. In NOT gate, there is only one input and only one output. So let's see the different types of gates from here onwards. So in this second part, we will see the OR gate, AND gate and NOT gate, how they are made, their Boolean expressions and their truth tables. First of all is OR gate. So as the name suggests, the OR gate, this particular gate will perform the logical operation of OR. In OR gate, the output of OR gate attains state 1, means these are the gates which performs binary operations for one or more than one inputs, and it gives binary output only a single, means they have more than one binary inputs and they give only a single binary output. So they will act as a binary source. Hence, this OR gate attains state 1, or you can say higher state, 1 or higher, if one or more inputs attain state 1. Now, in this type of gates, the input should or input may have two or more inputs, means this particular OR gate, the inputs, the minimum inputs are 2. The number of inputs can vary, means it can have 3 inputs also, but the minimum inputs in OR gate is 2. So if you are saying A is input, B is input and Y as an output quantity, so this particular OR gate performs this specific operation, means output Y would be equal to OR operation, or means plus, means A plus B. So you will get higher when one of the inputs will be in state 1, because the summation it means that only if it has both the quantity as 0 it will have output as 0, but if any one of them is non-zero then you will have output also non-zero. So the y or q is output and a and b is they are input. So let's see its truth table, that how you can construct its truth table. So its truth table is made from this Boolean expression. So this particular expression in logic gate terms, you can refer to it as Boolean expressions. So Boolean expression for OR gate is y or output is equals to a plus b, means input 1 plus input 2. This is how your OR gate looks like. The schematical representation of OR gate is something like this, means in OR gate there are minimum two inputs, input A, input B, but output will also be 1. So output, so y is equals to A plus B, or in other words you can denote it as a box in which if the one of the input is greater than or equal to 1, you will get output. But in case the both the inputs are minimum or 0, you will not be able to get any output. So in case when there is a input as 0 0, only and only then you will have output as 0. In the other cases you will have output. So let's see its input and output and its truth table. So when you will put 0 and 0 in here, means 0 input here, 0 input here, it will perform nothing but a simple summation procedure. 0 plus 0 would give you 0. Hence, when there are both the inputs as 0, you will get output 0. Now, when you have input A1, input A as 1 or higher state and input B 0 or lower, you will have output as 1, because 0 plus 1, or you can say 1 plus 0 is equals to 1, means output is non-zero. When you have the input 2 or input B as 1 and A is 1, A is 0, A is 0 and B is 1, you will have output as 1. And when both of them is higher, in its higher state, then output will also be higher. It will not be the typical algebraic sum of 1 plus 1 is equals to 2, because it is a binary representation. If both the quantity of input is non-zero, then you will have output as higher, not 1 plus 1 is equals to 2 or double something, but it will have output in its maximum stage. So it performs nothing but a simple summation operation over here. Means in the OR gate, if both the inputs are 0, then and only then you will have output 0. If one of them or both of them are non-zero, then output will have 1. So this was OR gate. Now let's talk about AND gate. Similar to OR gate, AND gate will always have two or more than two inputs. So it will have minimum of two inputs, and this is how your AND gate looks like in schematic representation. So in schematic representation, as you can see, this is the symbol for AND gate. These are the inputs A and B, and this is output Y. So AND gate performs nothing but AND logical AND operation. So the Boolean expression for AND gate is Y is equals to A into B, means multiplication of both the inputs, is the Boolean expression for AND gate. In the AND gate, the output of an AND gate attains state 1 if and only if all the inputs are in state 1. So from its truth table you can see that the output will have 1, or output will be non-zero if and only if both the inputs are non-zero or state 1. So this is nothing but it follows the AND operation. So let's make the truth table for AND gate. Now let's put 0 and 0 over here. 0 multiplies with 0 gives you 0 only. So whenever the input A and input B both are in 0 state, then output will be in 0 state. Suppose one of them is non-zero, then if A is 1 or B is 1, A is 1 and B is 0, then it will also give you 0, because 1 multiplies with 0 gives you 0. Also 0 multiplies with 1 gives you 0. So this is how one of them in non-zero will also give you a 0 quantity, because it will get multiplies with 0. But whenever both the inputs attains state 1, then and only then you will have output as state 1. So this was the operation for AND gate. It performs the AND operation, means A and B. Both are there, then and then you will have output A and B. While OR gate performs either or condition. If either A or B is non-zero, still you will have output. While in AND, it performs AND operation, means if and only if A and B, both of them are in state 1, will give you output as state 1. Now let's talk about NOT gate. What is NOT gate? So NOT gate performs nothing but not logical operation. This NOT gate also referred to as inverse gate or also called as inverse. So this is the unique or different gate from other logic gates as it has only one input. NOT gate has only one input. Please keep it in mind that only the NOT gate has one input and one output. The name NOT means it gives output totally inverse to input. NOT means whatever input is given is not will give you output. Means if you have input as 1, then it has output of inverse of 1. Means 1 is not. So it will be 0, and if you have input as 0, it will give you not 0, means 1. In a NOT gate, the output of NOT gate attains state 1 if and only if the input does not attain state 1. So whenever there is input as non-zero, output will be 0, and if your input is 0, then your output will be non-zero. Meaning if input is 1 or higher, then output is 0 or low. So its Boolean expression would be y is equals to not a, or you can say a bar, means not a. Means when you have 0, then not 0 means what? 1. If you have input as 1, then your output will be what? Not 1, which is 0. And this is how your NOT gate looks like. Means schematical representation of your NOT gate. In NOT gate, there is a bubble or you can say circle. This is something like diode, but this is not diode. This is logic gate not logic gate. In NOT gate, there is a arrow, and after that there is a bubble which represent the inverse performance. Whatever your input is will be inversed. If it is 1, then it will be inversed to 0. So this represents the inverse operation. So this is how your NOT gate looks like. Now the third section. In this section, we will see the combination of OR, NOT and AND gate. Means how combining two gates will give you another gate. Means the logic of both the combining gates will have quantity or quality which would be described as the another Boolean expression. So in this particular type or part, we will see NAND and NOR gates. Let's first see the NAND gate. NAND, it has N, A and D. You can see that it has a part of AND gate because it has A and D written over here. And this N stands for NOT gate. Means this is the gate which is combined with and NOT, which is made by combining the AND gate and NOT gate. So NAND is equals to NOT plus AND. This will first perform AND action, then result of AND. Whatever the result you are getting by applying AND gate operation to the inputs, then it will be converted to NOT, which will be the output of your NAND gate. Means in NAND gate, it will first perform AND operation, then the result of AND will be inversed, and that would be the final result of your NAND gate. So Boolean expression for your NAND gate would be, first it will perform AND operation, means A and B, and inverse of it, means not A and B. So Boolean expression Y for this NAND gate would be A into B bar. So this is how your NAND gate looks like. In AND gate, there is the presentation, and for NOT, you represent a bubble. So, combining these two factors, you have NAND gate something like this. Means, in only NOT gate, you have one input. In NAND gate, you will have two or more than two inputs. So, these are two inputs, A and B, and performing and not operation, you will get the output of your NAND gate. Means this is AND, this is not. Combining both of them will give you NAND gate. So let's see is truth table. Whenever there is output, there is input as 0 and 0. Input A is 0, input B is 0. What happens here is 0 into 0. You know that in AND gate only 1 1, means input A as 1, input 2 as 1 will give you output as 1. But this is the inverse of AND gate. So inverse of AND gate you can see over here that the output also inverse. In AND gate, you get 1 only here. So it will be inverted in NAND gate, resulting 0 as only 1 1, and you will have higher, or you can say state 1 result in each of these cases. So the truth table for NAND gate is inverse to the truth table for AND gate. So whenever there are both the inputs are 0, then you will have output as state 1. Why? Because 0 into 0 is 0, but not 0 means 1. Whenever there is 1 0 or 0 1, there would also be answer as 0 because of this multiplication operation, and also not 0 will give you answer as 1. But in case of both the inputs in state 1, so what happens here is 1 into 1 will give you output as 1, but here 1 and inverse of 1 gives you output as 0. So this is the truth table for non-NAND gate, which is the inverse, or you can say total opposite to the AND gate. So in NAND gate, the output attains 0 if and only if both the inputs are in state 1 or higher. The next one combination is NOR gate. So in here you can see NOR gate as here is OR and here is NOT. So NOR gate is a combination of NOT gate and OR gate. So NOR gate is equal to NOT plus OR. This will first perform OR action, then the result of OR will be converted to NOT, which will be the output of NOR logic gate. So NOR logic gate is made up by performing first both the input first perform OR operation, and the result of OR operation will be inverted, and that would be the final result or the result of NOR gate. So the NOR gate's truth table is totally opposite to that for OR gate. As we discussed earlier, that in NOR gate only the output will be in 0 if both the, or you can say if and only if both the inputs, means input A and B, both are in 0 condition, then only then you will have output as 0. In the three other cases you will have output as 1, but this is NOR gate, so this is the total opposite. So in here, what you are getting is you are getting output 1 only and only one time, and all the other three cases has 0 output, total opposite to OR gate. So Boolean expression for a NOR gate is A plus B bar, or you can say not A plus B. First it will perform the OR operation, means A plus B, and the result of this will be inverted. So let's see how you can build this table. Put 0 0 over here. 0 plus 0 would be 0, but the inverse of 0 would be 1. So at the time of 0 0 you will have output as 1. In the other two cases of 1 0 and another as 1, so if it is 1 0 or 0 1, in these two cases what happens is the summation remains 1 because one of the quantity is non-zero. So your answer would be 1 over here, but the inverse of it, inverse of 1, would be what? 0. And in case of both the inputs as non-zero, it will give you also, it will give you also as 0, because 1 plus 1 would be 1, but the inverse of 1 would be 0. So this is how you get the truth table of NOR gate. Now how you represent NOR gate? So NOR gate is nothing but the combination of OR gate and NOR gate. This is how you denote or express your OR gate, and this is how you represent your NOT gate. In NOR gate, the inputs are minimum 2. It can increase, but the minimum inputs are 2. So the combining both of them would give you this. So this is how your NOR get represented, means it has two inputs and one output. This is or this is not, and combining them will give you as result of NOR gate. Now expression, Boolean expression is something like this: A plus B bar. Means whatever you are getting input as A plus B, this would be inversed to get NOR gate. So this was about NAND and NOR gate. So here we have reached the fourth and last section of this particular lecture, which is exclusive gates. So in this particular section we will learn that how you can build exclusive gates and what are the truth tables and their Boolean expressions. So let's start with first XOR gate. That what is XOR gate? So XOR gate is also known as exclusive OR gate. The full form, or you can say the main term, is exclusive OR gate, and you can also represent it as X and then or XOR gate. So in XOR gate what happens is, in this particular gate, whenever both the inputs are same, keep in mind that whenever both the inputs are same, either 0 or 1, 0 0 1 1, means both of them are in state 0 or both of them are in state 1, then and only then the output would be 0. If any of them is non-zero, then you will get output as non-zero, or you can say state 1. So this is how your schematic representation is done for XOR gate. This is OR gate, simple OR gate, and before it, it is shaped. So this is known as XOR gate. So as you can see in XOR gate, the input 1. Here two AND gates, 1 and 2. Two AND gates are used, two NOT gates are used. First these four gates are used, and then after there is a OR gate. So in the end there is OR operation. First there will be uh, you can say AND operation means the multiplication of both the inputs and performing its inverse, or you can say NOT. So first, in this type of gates, first and NOT gate operations are used, and then after the result of it is performed under OR gate operation. So the Boolean expression for this kind of gates, or you can say for XOR gates, are a b bar plus a bar b, means this is the multiplication and then after OR operation, and the Boolean expression is denoted something like this: a plus b, but in the positive sign or in the plus sign it has a circle around it. So this is how the Boolean expression for XOR gate is represented. So, as we discussed earlier, that in XOR gate, the output will have state 1 only. One of them or one of the input is in state 1. So, in an XOR gate, the output of two input XOR gate attains state 1 if one adds only input attains state 1. From the truth table, when only both inputs are different, output will be high or 1. When both the inputs are same or 0 0 or 1 1, the output will be low or 0. So in the formation of XOR gate, there are two AND gates, two NOT gates, and this functionality gets added up to OR gate. So first, the input is one is fed to AND gate and another is fed to NOT gate of the other's AND gate, and the input B is fed directly first to NOT gate and then the another AND gate. So this is how your XOR operation is made as AB bar plus A bar B. Now the second exclusive gate is XNOR gate. So in XNOR gate, what happens is XNOR gate is the NOT of exclusive or you can say inverse of exclusive OR gate, and XNOR gate is also represented as X and then NOR. So XNOR gate is not XOR. So you will get output whenever both the inputs are in same state, whether they are 0 0 or 1 1. Then you will get output as high or as state 1. In the XNOR gate, the output is in state 1 when both the inputs are same, or you can say both are zeros or both are ones. The output of XNOR is equals to inverse of XOR gate. From the truth table, when only both inputs are different, output will be low. And when both the inputs are same, zeros or ones, output will be high or 1. So this is how the truth table formation gets done whenever both the inputs are same, means 0 and 0. Input A is 0, input B is 0, then you will get output as high or 1. If you have both the inputs different, means one is 1 and another is 0, or A is 0 and B is 1, then you will get output as 0 or low. But when both the inputs are high or in state 1, A also in state 1 and B also in state 1, then you will get output as high or 1. This is how schematic representation stands for XNOR gate. This is simply nothing. This part is XOR. And applying a bubble or circle after this XOR gate gives you the representation of XNOR gate. Means whatever the result of XOR get inverse or becomes inverse in the output of XNOR gate. Now Boolean expression for XNOR gate is output or Q or Y is equals to A XOR B and its inverse. So inverse of A XOR B. And this is how you can build an XNOR gate, which is a first is NOR gate, then another is AND gate, and the result of these two gates is fed to OR gate, and hence you can get output as XNOR gate. So another representation would be Q is equals to A into B plus A bar into B bar. This is how you can give a expression for XNOR gate. So this was all about logic gates. We'll see you in the next lecture. Thank you.